Oh, g'day everybody, where's Wally here? Well, today we will be ruining the whole year of the sextant. I warned Mitchell months ago when he said that he was dropping anchor on this, that would be a fatal flaw. But would he listen to me? Well, if by blocking you mean listening, then he listened very well indeed.
You get it, Wally.
So I saw Nathan Oakley misunderstand Ruhif's most excellent adventure into the dip angle. You flatties that bang on about sextants, well, this is the downfall of the year of the sextant.
This is why this sextant is the #1 flat earth proof, and it has not been disputed. It has not been debunked. 2021 is the year of the sextant. It may well be 2022 be the year of the sextant too. It cannot be debunked.
And this is usually the point where the flirfs just declare that you can't do Trigon stars, or that we don't know what they're made of, or some other irrelevant bullshit that makes no sense. Although I guess the good thing to come out of this sextant argument is that we've finally convinced the flirfs that we can look up in the sky to work out the shape of what we're standing on. Okay, so we've just seen how the trig fails on a flat earth, and here's how it works on a globe. As you can see, it's utterly trivial to show that the angle to Polaris matches your latitude.
This is a good one. 90 degrees right there. And obviously all the parallel rays are forming different angles there.
And it also explains why you can't see it from the southern hemisphere, because there's a whopping great big lump of planet in the way. But as usual, the flirfs will just hand wave everything that doesn't suit their narrative and just throw around buzzwords like perspective, as if it actually explains anything. So with that in mind, I have a challenge. If this is the year of the sextant and it's the #1 flat earth proof, then all I'm asking you to do is show two things. Number one, how do you derive the horizon dip correction if the earth is flat? And number two, how do you derive the 1 degree per 60 nautical miles if the earth is flat? I guess I will not be holding my breath for genuine responses from the flirf community.
The higher our eye, the bigger the amount of the dip angle. So dip is purely a function of our height of eye. There it is right there. Dip is purely a function of our height of eye. Nothing to do with a globe, nothing to do with curvature, nothing to do with the horizon dipping away from us. No, dip is purely a function of our height of eye, right there in the reference. Dip is purely a function of the height of our eye. So if that height is known, dip can be calculated. And we've seen the table in the Nautical Almanac.
Here's your slide that they made fun of, showing the very same thing. And they're making fun of you, Mitchell, but here's a navigator on the ship, and he's got this height difference to correct, right? And how does he do that? Well, he goes to the Nautical Almanac or the AR Almanac, and he goes to corrections to be applied to marine sextant altitudes. Correction for dip of the horizon to be subtracted from sextant altitude. Subtracted always.
The horizon dip formula uses a radius pretty close to 7/6r, which kind of shows that it's being used in the real world and wasn't just pulled out of Mick West's ass.
You're actually relying on R. I bet you didn't know that. Because the dip corrections in the Almanac, they are all based on R. And by R, I mean the radius of the Earth. So funny. We all knew this, but we do love to toy with you guys, and we wait to see what else we can get you to say. But you lot can't do that on a pizza platter without using R in the form of a dip correction. Want to have a dip correction for your horizon sighting? There's a hidden R in that.
Now stand aside, worthy adversary.
'Tis but a scratch.
A scratch? Your arm's off.
No, it isn't.
Well, what's that then?
See, we don't have a problem with you measuring angles. Even the housekeeping question that Nathan had to add. What was that again? Can you show how you get an angle from a curved adjacent? Well, Nathan, that does sound just a tad straw-manish, doesn't it? But of course, you don't need to just use a local horizontal plane. You could use a vertical. Well, you could also use an artificial horizon, or, as 10th Man said, how about a bobble sextant? If it's good enough for aviators, it's good enough for all of us.
Anyway, back to my point. You're on an airplane. 30,000 feet above the earth. You can't see the horizon. How do you do what the mariners do on the ocean up at 30,000 feet? You have to mirror what they have. What do they have? A flat baseline. So you put spirit level into a sextant, you create that flat baseline, then you bring the sun into that center of that bubble and then say mark. Much like the sailor does when he brings the sun to the edge of the horizon, rocks it until he gets a true vertical. And they go through the next process is all the same.
So I think that shoots it right fair and square in the foot. Yet another rug pulled right out from under your little feet, mate.
Victory is mine. We thank thee, Lord, that in thy mouth...
Come on, then.
What?
Have at you!
You are indeed brave, Sir Knight, but the fight is mine.
At this point, we need the experts, the professionals that actually use these things. Like we're just amateurs here. We're just saying how the sextant works. We're just telling everyone how it proves the flat Earth. But we need the professionals like Wolfie who actually use this in a professional setting, in an emergency setting, when all else fails, when you've got all that technology, when all else fails, he pulls out the sextant and the sextant never fails. So at that point, we need people like Wolfie 6020, people who are using the sextant to come out and just let us know how we're using the sextant, especially at altitude. That's how I want to know. I want to know how we use the sextant at altitude. Are we looking at the horizon? Obviously, the horizon changes so much. You've got a massive dip correction. Are you accounting for the dip correction, Wolfie? Are you bringing that measurement down to the geometric flat plane? And that's where the conversation needs to go. Are we using the horizon with the sextant at altitude? And are we accounting for the dip angle? Now let's go into the dip angle, Brian. I think we've been alluding to it for a bit.
Yeah, exactly. And I would like Wolfie to maybe make a video on that, because I'd like to know what it is he does with that sextant at 6 miles up in the air. Yeah. We'd all like to know.
Yeah, because what we're going to be talking about right now is the dip angle. You need to correct for the dip angle. And if you're not correcting for the dip angle, you're not getting a true reading with the sextant. I think everyone can agree on that.
So, as Mitchell says here, you have to adjust the reading back down to the surface or else it's wrong.
What we're doing when we're accounting for the dip angle is accounting for the height above sea level. Because when we account for the height, you can see that it brings the error, the dip angle error, down to the geometric plane. And that's why they don't want to address this. Because upon correcting for the height, correcting for the dip angle, we are physically measuring with the sextant the geometric plane. It brings it down to the surface of the Earth with the flat baseline, with the 9-degree angle, and this is only achievable on a flat Earth.
Well, my mate Sean Hawkins, he decided he'd take them to task over their dip correction and why they're doing it. And he, as Sean pointed out, flatties don't really seem to know what they're doing and why they're doing it.
Just thinking about how 10th Man Rising claims that when you correct for dip angle, when you correct for your downward looking at the horizon, you have to move this line down to here. So you're changing this angle instead of this angle. So in actuality, you bring the line up to horizontal, which gives you your angular measurement. Gives you your angle.
Good stuff, Sean. And Wolfie, seeing that flatties really don't have much of an idea of how to do celestial navigation with a sextant, decided to throw out one of his classic old challenges. He started at $500 for someone to show them start to finish. Celestial navigation with a sextant. The full process.
Emma, what do you have there?
The sextant.
The sextant? And what are you doing with it?
I'm looking at the stars.
You're looking at the stars? Well done. So I find it quite amusing to see how many flat earthers are talking about the sextant in recent weeks. They've made numerous videos and they spend hours discussing the sextant. But they're forgetting the most important part, actually using the instrument to obtain their position on the Earth. I believe that none of these flat earthers actually know how to use a sextant, and as usual, they're just talking about things they don't really understand. So in this video, I'm going to put my money where my mouth is and offer a challenge to flat earthers to prove that they actually do know how to use a sextant.
No one has taken it up yet. A few guys have chipped in a little bit of pot sweetness. I think it's up to over $4,000 now. So where are the flatties? Do they not have any confidence in their own ability either? You think this would be bread and butter for them about now? They are so confident that they can do it.
That's the knowledge I've been sharing, and now everybody else is doing. And I say, everyone, go to the sites that are available. There's hundreds, if not thousands, of videos. I've watched every one of them 10 times. All the significant navigators with navigation YouTube channels who are showing you every step of the sextant. And then it starts breaking apart when you ask the right question.
Well, guys, I think that's pulling rug number 3 right out from underneath you there.
Look, stop that! Chicken! Chicken! Look, I'll have your leg! Right! Right, I'll do you for that. You what? Come here!
However, Flurfs and Celestial Navigation have got bigger issues than this. That jolly R that flatties will never let us use at all. You're presuming the globe. Assuming R, you fundy. Are some of their favourite chants. Well, isn't it amazing where R shows up? We just saw it underpinning the whole dip correction thingy. That black swan, every time the Muppets mention how far the platform is away from the beach, they used Google Maps to measure it, didn't they? Anacapa Rock, measured on Google Earth. You know, that map that shows Earth curve if you zoom out far enough.
Why are you asking me something? So you don't have any Earth curve in your map? Don't ask me something.
I've not met a single cartographer.
Don't tell me who you've met. Just confirm you haven't got drop in your map.
Yeah, that one. There's R in that. Nautical Almanac. Based on R. What you say, Wally? That's right, Nautical Almanac. Based on R. So what is actually happening when we do celestial navigation? We measure an elevation angle to the celestial object. That's simple enough. So simple even a Flurf can do it. But what we really want is the angle from vertical anyway. So measuring the vertical is actually better. Here, let me explain why. What are we really doing when we use the sextant for celestial navigation? Let's try this simple thought experiment. The navigational star of interest is right overhead. Okay, 90-degree elevation. Where's the GP? 0 degrees difference from the sight to the star to our zenith, so the GP is right under our feet. Now wait 4 minutes, do the sighting again. You will find that the star has moved exactly 1 degree. Now the almanac gives you the distance or the range of 60 nautical miles. Wait another 56 minutes or 1 hour from when the star was directly overhead. Now the star is 15 degrees from our zenith.
A 15-degree-per-hour drift.
Thanks, Bob. So now the almanac gives you the distance or the range of 900 nautical miles. So just look it up, mate.
Way that we get the D, it is in the Nautical Almanac. Yeah, if you're getting a 30-degree angle to a known navigational star, you just look it up in the Nautical Almanac and you know how far you are from that GP. We're not doing calculations here. It's already in the book, mate. Yeah, you can do calculations. You can get that distance using a calculation, but...
Now, you said you can do those calculations. Have you ever looked at how and why they are done? Seems Mitchell, or rather 10th Man, if he has actually ever done a full sextant celestial navigation from start to finish, they get to step 2 and then they cheat. They get an angle via the Nautical Almanac and voila, they have a distance to the GP. Now this is where it gets interesting. Those figures in the Nautical Almanac, they are converting the angle to a distance. So then you can go on and complete step 3, the trilateration step. So it seems to me that flatties are treating the almanac a bit like the Book of Spells. They say the magic words, "O great almanac, wise art thou, we look upon thy great star Alpha Canis Majoris at the very hour of 2021, November the 21st at 1720 UTC, and we saw a corrected sextant elevation of 34 degrees and 21.9 minutes. Please reduce unto us the distance of the GP that pleases thee. Allow us to rinse and repeat this thrice. The number of the sightings shall be 3. 2 sightings we shall not take unless we proceed directly to 3. 4 sightings is right out. Where are our intersections of possible positions? Oh, mighty circles of equal elevation. Well, I just pop all that data into a website. It does it for me. And it shows 944 nautical miles. So that got me thinking, how does the angle of the star become a distance on the surface? Then I saw this.
At any given moment, every celestial body may be mapped to the Earth, as there is one point in the terrestrial sphere where the celestial body lies directly overhead. This is called the celestial body's geographic position, or GP. If you were standing at the geographic position, the celestial body would be directly overhead, known as the zenith. Measured from any point on the horizon, the angle of this celestial body would be 90 degrees. Astronavigation allows for determining your geographic position by measuring the angle from the local horizon to the celestial body and determining a line of position, which is actually a circle on the terrestrial sphere. Locally, however, these circles can be treated as straight lines. By obtaining a line of position for 2 or more celestial bodies, these lines should intersect to mark your position. This process involves knowing the geographic position of the celestial body at a given time and solving some spherical trigonometry. By using publications produced by the US Navy and their UK partners, spherical trig calculations are replaced by tables, and this process is greatly simplified. Only addition and subtraction are needed to complete a sight reduction form and obtain a line of position.
Oh, so the Almanac is to simplify spherical maths to just additions, subtractions, and finally a multiply by 1 nautical mile per minute of angular separation. Well, that seems super easy, barely an inconvenience. Seems to me that the Almanac is a globe tool. Well, that's interesting. Let's see if that's true. So, step 2, the Nautical Almanac, I downloaded code that prints the Almanac for any year that you wish. And here is the code for that cool website doing the sight reductions. So let's have a look at that. Oh look, global variables are plenty. And what's this one here? Radius. Oh, that looks like a very familiar kilometre value to me. So now we see that the Nautical Almanac, made by astronomers, as Mitchell says, it's full of R-holes that preclude any flattie using it.
It's because this book is made by astronomers, the Almanac. We're talking about the Almanac. This book is made by astronomers. And as astronomers don't talk about latitudes and longitudes, they do talk about hours and angles.
Well, hello Mitchell, how are you? So I hear that you fancy yourself as an expert in navigation using a sextant. Well, you see, Mitchell, there is this little thing called latitude, created by Hipparchus in 190 BC. And just quietly, it's based on a sphere, Mitchell. And then, Mitchell, there's that staple of globe-based navigation, namely 69 statute miles per degree of latitude. That is the pole-to-pole distance of 12,436.8 miles divided by 180 degrees. And that equals 69 statute miles per degree of latitude. It's not a coincidence, Mitchell. So sorry, Mitchell, but you are going to need a globe for that.
So it seems now that we've taken away the Nautical Almanac from the flat Earth, because it's full of R's, they're left without a leg to stand on, as they would just be resting on their R's now.
You're a loony. The Black Knight always triumphs! Have at you! Come on, then. Oh. All right, we'll call it a draw. Come, Patsy. Oh, I see.
Say goodnight. 2 is the age of the sextant.
What are you guys going to do now? Seems celestial navigation, the year of the sextant, didn't even make it to its first birthday. Oh, how sad is that? So unless flat earthers can figure out a way to do the trigonometry correctly that works on a flat earth, and they're going to need a model for that, I guess you're not going to be able to play with sextants anymore.
Hey Mitchell, you want to do celestial navigation with a sextant? You're going to need a globe for that.
In summary, you guys are going to have to be so careful from here on in because Actually, we live on a globe. There are R-holes everywhere and they're embedded in everything you do, and it's not always apparent, and you guys really aren't smart enough to figure it out. Truth be told, you don't really care, do you? You'll do whatever it takes to get the answer that's flat. Even when we demolished your chant rant, you guys still carry on as if nothing ever happened.
Running away, eh? You yellow bastard! Come back here and take what's coming to you! I'll bite your legs off!
You don't know when you beat.